Hello and welcome to the second half of week 1 for Math 131. Just as a quick reminder, your goal for these videos and this lesson is to combine what we have in the lesson here with this video to fill out your copy of week 1 notes in order for you to get a good understanding of the material such that you can complete week 1 assignments. Both your notes and the assignment count towards your grade for Math 131. For the second half of week 1, we will be talking about packages, arrays, and data frames. So let's jump to it. Because we're going to start talking about packages in Python, I'm going to show you the commonly first two lines of most of our assignments. You're going to have a line that looks like this, which calls to the underlying computer that runs your Google Colab notebook. The underlying computer's program named pip, and it's asking pip to install and possibly update the Python packages NumPy, Pandas, and Plot9. That's going to take a second to run, so while this runs, I'll explain what packages do in the world of Python. In order for data science to use Python effectively, people have gotten together and created standalone packages that help us do common tasks in the world of data science. So NumPy has an incredibly popular data structure, much like a list that we'll explore soon in this video, named array. So the NumPy package is going to allow us to work with a popular data structure named array. The Pandas library has another common data structure to data science named a data frame, and actually Pandas builds off of NumPy. And Plot9, you might guess, is used for plotting. So what we need to do at the start of these notebooks is to update these packages such that Google Colab can use the latest version of these packages available, and that's what this code is doing here. Anytime you see this cell or a cell like this at the top of a notebook, you should run this cell, and then I'll remind you, you should then click Runtime Restart Session. In the future, I won't leave such a note like this here. It'll be blank like this. But for now, it is a quick reminder to click Runtime and Restart Session after you've asked pip to install and update some packages for us. As long as you've done this, then everything should work fine, and you don't need this output here, so we can clear it, and we can immediately jump to importing these packages so that we can use them. So this line of code is going to import the package Plot9. We'll also import the package NumPy, and we'll reference NumPy as NP later on. We'll also import Pandas and reference Pandas as PD. It is common to, in the world of data science, to reference NumPy as NP and Pandas as PD in general. So let's move on to NumPy. NumPy has a data structure that we will access through the NumPy package and the function within that package named array. It takes one argument, and it's commonly a list. So here we'll assign into the variable a NumPy array that is created from a Python list of floats. That's what the decimal place, that's what the dot is doing at the end of all those integers, is telling Python to create a list of floats, such that we now have an array of floats, 1, 2, 3, and 4. Arrays are very much like Python lists, except these NumPy arrays are homogeneous data structures. So all the elements of a NumPy array must be the same type, unlike a Python list, where all of the elements of a list can be different types if you want. With these arrays, you can do all sorts of fun things that you can imagine shows up in the world of data science and statistics. You can calculate the mean of all of the numbers in the array or the standard deviation, or you could even ask for the size of an array. So in this case, our array little a has 3 elements in it. So the size is really just the name of the number of elements in an array. There's other functions in NumPy, like ones, which will create a multidimensional array for us. So in this case, we have a multidimensional array, specifically 2-dimensional array, where the first dimension has has size 2, and the second dimension has 3. So you can see here we have 2 rows and 3 columns of ones in the 2-dimensional array, capital A. And so we can do fun things like, let's create a 2-dimensional array A of shape 2 by 3, and then let's take that 2-dimensional matrix, 2-dimensional array of ones and multiply each element by the mean of little a. Because the mean of little a is 2, we're going to take 2 and multiply it element-wise by the 2-dimensional array A. Since 2 times 1 is 1, you can see we get out a new array of the same shape as capital A that consists of just 2's. And there you go. This was our introduction to the data structure array in the package NumPy. As a quick lesson in Google Colab, sometimes we might want to print the value of some function, like the shape of A, and output the size of A, all from the same cell. So if you want to explicitly print more than one thing in a Colab cell, you have to put the function print around whatever you're trying to print if you want to print that thing and it's not showing up as the last line of code in the cell. Let's see if we can say that again with a better example. Without the print statement, notice that NumPy's function shape looks like it doesn't return anything at all. In fact, it does, but Google Colab will only print things automatically if they are on the last line of a cell, and it won't print stuff otherwise. You can force Colab to print things that don't show up on the last line of a cell by explicitly wrapping them in the print statement. So here's a friendly reminder of some features of Google Colab. Meanwhile, we are reminding you about the shape of A and the size of A. When you have a multi-dimensional array, like capital A, the size is effectively the product of the lengths of the dimensions. Cool. Let's move on. Next, we'll introduce data frames. Let me go steal some code I have planned ahead here. In order to help us understand data frames, we will use the data frame named diamonds built into the package plot9. Well, technically it's from the subpackage data within the package plot9, but that's not for today. We're going to use this data frame named diamonds, and I'm printing it out here so we can see it before we start talking about it. A data frame, like the one named diamonds that we've imported from the package plot9, is a 2-dimensional data structure of heterogeneous type. So notice we have floats and what looks to be strings and more floats. And over here is some integers, some ints. So a data frame is like a 2-dimensional data structure, but different than a NumPy array. Each column of a data frame can be of different types. So floats, ints, and strings are the most common types within the columns of a data frame. So within each column, they all have to be the same type, but across columns, you can have multiple different types. And this is a data frame. I'm not going to get into all the details within this video that show up in week 1's lesson, but I will point out some of the more important ones in my opinion. So for instance, diamonds has a function associated with it that you can get at by going .loc, and you can ask for, let's just say, the column depth. So we're asking for the location of all the rows, that's from 0 to 53,939, all of the rows with just the colon and just the column depth. So you can see we print out just that one column from the data frame. Now, this is some code you use to extract a column from a data frame, but what you have here is effectively, though not truthfully, is effectively a NumPy array of floats, which means you can do things like we've done before, and you could calculate the mean of that column depth, or you could calculate the standard deviation of that column depth, or of course, size, like we've seen before. You can effectively treat each column of a data frame like a NumPy array. Now it's a little annoying to have to type this out multiple times, so we could use our knowledge of variables and create a new variable that is just depth. And this will run all the same as we did before, but you can see by reusing the variable depth that we just created here, we now have saved ourselves a bunch of coding throughout. Okay, let's continue with accessing elements of a data frame more than just a column. You could also go from the data frame diamonds, access the locations of, let's say, all rows and multiple columns. Notice we are now using, instead of a string for the column labels, we're now accessing the columns by a list of strings. And that will give us a new data frame. We now have a data frame of 2 different columns. Each column has the same types within that column, but across columns we have different types. So here we're accessing all the rows and the 2 columns specified by depth and cut within that list. We could further use what we've learned from indexing lists to index over just a slice. So now here we're going to get rows 0, 1, 2, 3, 4, all the way up to and including 10, and the columns depth and cut. So now you can see we've taken out like a subset of the data frame diamonds. One thing we absolutely must note here is slices index starting at the left value, starting at the left of colon and include the right of the colon. This is different than indexing lists with Python. When we were indexing lists with Python, it would have excluded the value 10. But you can see here in Panda's data frames, we are including the value 10. That's a little bit annoying, but it's something you have to pay attention to and deal with as you go. Let's do something fancy now to help us see if we can start working up towards what would be a fun data science question. Let's say I want all rows from the column cut where they are equal to very good. Okay, this line of code is saying, give me the entire column of cut, so indexed here, and it's asking which of the rows are equal to very good. So you can see row 0 is ideal. That's not equal to very good, so that gives us false. Row 1 is premium. That's not very good, so that gives us false. Rows 5, 6, and 7 and 9 are very good, so they should return true. Now notice we don't have rows 5, 6, and 7 printed here. By default, rows 0 through 4 are printed, and then if there's more, it'll give us this dot, dot, dot. And then continue on at 53,935, but effectively like the last 5 rows. So if we wanted to verify what this line of code is doing relative to these two, remember, we could just do something like just print out for us the 0 through 10th rows, where we expect rows 5, 6, 7, and 9 to be true. 5, 6, 7, and 9. That's excellent. Once we verified, we can go back to what we have before. And let's store this into a variable named idx. In my head, I'm thinking index. We're going to use that variable idx as our slice to say, give us only the rows of the column cut where the cut is very good. And it's going to leave out all of the other rows. So notice rows 0, 1, 2, 3, and 4 are excluded from this line right here. So IDX is an index of Booleans for every value that is true, like rows 5, 6, 7, and 9. We're going to take those rows from the column we've specified here, cut. And for any value of IDX that is false, we're going to exclude those rows from the column cut. But what's cool about this is we could say, hey, give me only the rows associated with IDX for the column depth. And so now we can say, what is the mean of the column depth where the cut is very good? And that is an interesting answer. From relatively simple code, we can find the mean of the depth. Honestly, I don't know what depth means. The mean of the depth for only very good diamonds. But we could do one better. We could compare the mean of depth for very good diamonds relative to the mean of depth for not very good diamonds. So this little character here is a tilde. Shift button to the left of 1 is a tilde. And we're going to say negate, that's what tilde means, negate the Boolean values stored in IDX. So anywhere, oh, I've never seen that before. Anywhere IDX was previously true, the tilde is going to make the true false. And anywhere the Boolean index IDX was previously false will now become true. That's what this tilde is doing. It's like flipping all the trues to falses and all the falses to trues. So if we calculate the mean of all the not very good diamonds depths, we can now compare the mean of very good diamonds depths to the mean of not very good diamonds depths. Well, that was a quick introduction to Python packages. Some of them create new data structures for us, like NumPy arrays. Some create multi-dimensional data structures, like Pandas data frames consists of rows and columns. And with that, we can start answering incredibly useful questions that allow us to compare different groups of things by means or standard deviations or what have you.